Okay, so yesterday, I talked about some quantum mechanical examples and quantum states, and how to classify the quantum states. And we have seen that if the state is pure and bipartite case, then you can always canonicalize the form of quantum states in the following way. So it's called Schmidt decomposition. And what we have done is that by changing the orthonormal basis, you end up with a canonical form. Maybe I didn't write it here, but okay, basically, okay, so you end up with a canonical form. So psi is now takes this form, and I think square root here, and times IA times IB. So this is a Schmidt decomposition. And I runs from 1 to the minimum of the dimension of A and dimension B. So this is the Schmidt decomposition. And okay, we basically order these Schmidt coefficient in the descending way. And then, so now we can compare. So we can introduce an order between quantum states. So using this Schmidt vector. And this is a partial order. And we have several examples here. And so we have seen that, okay, by using the, okay, thanks to the Nielsen's majorization theorem, so we can answer to this question. So given two states, two pure bipartite states, psi and phi, so when can psi be transformed into another state, the other state phi, by only using LOCC, so that the quantum operation you can use. And okay, yesterday, okay, I had a wrong expression here. So, okay, so basically instead of directly using LOCC, I gave you the expression of the separable operation, and I had the wrong expression. So this is a new one. So this is this condition. Yeah, yesterday I wrote the wrong condition, but this is the correct condition for the separable operation. And okay, I was asked many questions about what's the meaning of LOCC, especially, so what the CC is. So I try to make a few comments about it. So, okay, so from this definition of separable operation, so it's clear that this operation implements locality. So namely, so you have a tensor product form of the operator AM times BM. So this is this respects the locality of the operation. But the question is, so how do you implement CC? Okay, let me consider one simple example. So suppose that Alice performs some operation AI, and then so she sends her outcome, so her results. So depending on I, so she sends the results. So which depends on I to Bob to B. So then, also by classical communication. So then, so Bob also performs his measurement, some operation. But he knows the result of Alice. So so now he can perform some operation which depends on I, but he also has some operation depending on his measurement, so the J. So he has, okay, now his operation depends on two parameters, I and J. So you end up with, okay, so now, so previously we have AM times BM. as operator. But now, so you have AI times BI, BJ with superscript I. So you can relabel the I and J into one vector. So for example, so M can be some vector or matrix combining I and J indices. So LOCC of this type is apparently a subset of separable operation. Okay, this is one example, and there are many types of LOCC, but the idea is completely similar. So this is a meaning of LOCC, and now this is the Nielsen's majorization theorem. So for bipartite pure states, so psi can be transformed to the other state phi under separable operation if and only if the Schmidt vector of psi is majorized by the Schmidt vector of phi. So this is a very concrete answer. And so yesterday, so this is good. So this theorem is very good, but you need to know all the Schmidt coefficient to answer to the question. So that's a non-trivial task. So it would be nice to have one function, so scalar function, on the space of separable, space of pure bipartite states, such that it quantifies the order. So namely, so this direction f is a kind of height function. So this is height function on the base space S, so on S. So you have a height function, and if you compare the heights between two states, and if one of them is higher than the other, thank you. Yeah, if one of them is higher than the other, then it is possible to find some. It would be possible to find a operation which transforms psi to phi. But I think I emphasize that such a function does not guarantee the existence of the operation such that phi can be transformed to phi. It implies that So basically, the height function satisfies this condition. So if x is majorized by y, then f of x is greater or equal to f of y. So this implies that if fx is greater than f of y, then it does not necessarily mean that x is majorized by y, but it means that y cannot be majorized by x. So it's a bit tricky. So namely, so if you compare the height of two states, and if one of them is higher, then you can convincingly say that there is no operation which transform phi to psi. So this is a concrete statement, but there might exist some operation, LOCC or separable operation, which transform psi to phi, but it's not guaranteed. These two states may be kind of isolated and not comparable in some cases. So this is what we have done yesterday, and so to quantify the order, so we introduced quantum information measures, and so there are several postulates for the measures. So one is a monotonicity. Of course, we want to quantify the order. So it should respect the order, the partial order. So when psi is transformed to phi under LOCC or separable operations, so the measure, so given by this function f, decreases. And we also postulated that the second assumption. So this is the vanishing for separable states. So since separable states is by this is our definition of entanglement. So separable states does not have any entanglement. So for separable states, we want to offset the function. So this is the choice of the origin of the function. So okay, in general, for entangled states, so f, okay, we will see that okay, f is basically the positive. So and it quantifies the amount of quantum entanglement. Okay. And the third postulate is the convexity. So this is just a mathematical reason. But if f satisfies this convexity, so you can prove a very non-trivial inequalities, which turns out to be very useful in applications, even for quantum history. And I quickly introduced yesterday the relative entropy. So this is relative entropy itself is not the quantum entanglement measure, but you can construct nice measures from a relative entropy. And the relative entropy is a kind of distance, so between two quantum states. But this is not complete distance because, okay, by definition, okay, I gave you a definition. Okay, S of, okay, given two states, rho and sigma, it is defined in this way. And apparently, it's not symmetric with respect to the exchange of rho and sigma. So this is not symmetric, so it does not satisfy the axiom of distance. But it has very nice several properties. So one of them is monotonicity under the separable operation. Well, more generally, so separable operation is a subclass of so-called CPTP operation. And actually, the monotonicity holds even for CPTP operation. So CPTP means completely positive and trace preserving. So this is completely positive and trace preserving. Anyway, this is probably most general operation you are allowed to perform in quantum information theory. And I do not give you the definition of completely positive, but okay, trace preserving is very natural because after performing some operation, so you want to okay, basically, so suppose that the trace of rho is normalized to be 1, and then you want to keep the probability to be 1, okay, total probability to be 1. So even after the operation, so okay, so it means trace preserving means that lambda of rho, okay, if you take a trace of lambda of rho, then it is 1. If trace of rho is 1. Okay, so trace preserving means suppose trace of rho is 1, then trace of lambda rho is 1. So it is just a meaning of trace preserving. And the completely positive means that, okay, originally, so we have a positive operator. So rho is supposed to be a positive operator. And even after the operation, it should be a positive operator, because otherwise we cannot interpret it as a density matrix. So this is basically the meaning of completely positive. And under such a general operation, CPTP, the relative entropy is known to degrees. And intuitively, so we have a space of quantum states, and we compare the distance between two states, rho and sigma. And after any quantum operations, so the distance between them always decreases. And I will give you some more intuitive interpretation of this monotonicity later. So when I talk about the relative entropy in quantum theory. And also, there are a few properties. Lambda is not necessarily unitary. Yeah. So there are a few properties I should write here. So there is relative entropy is known to be positive, so positivity. So this is important. So for any two states, rho and sigma, the relative entropy is non-negative. Okay, so I should say that it's non-negative, so non-negativity. And so if relative entropy vanishes, so then rho and sigma are equal, and the converse is also true. Okay. So in this sense, this is roughly a measure of distance on the quantum states. So, and also, I'd like to give you one example of completely positive CPTP operation. So this will be useful in quantum field theory. Okay, so the example, a very important example of CPTP is the partial trace. So partial trace means that, suppose we start with, for simplicity, let me consider some tripartite system, and A, B, C, and originally we are interested in the union of A and B. And so we are given some density matrices. Suppose, so we are given density matrices rho and sigma on the union of A and B. So this is our original system, so we're interested in. But we perform some operation, so-called partial trace, and it is defined as follows. So T is the identity operator on A and times a trace on space B. So if we perform such an operation, then you end up with just a system A. So after taking partial trace, so rho of AB, sorry, so I don't need sigma here. I only need rho on one quantum state. Then rho A union B is now mapped to rho of A. Okay, so this is a simple example. So this is called a partial trace, and even, this is of course a part of, some example of CPTP operation. So in such a partial trace, the relative entropy is also monotonically decreasing. Sorry, this is sigma. Okay, so basically the monotonicity means that, once you restrict your measurement or observation in a subregion, then it becomes harder and harder to distinguish two quantum states, because you have less operators to distinguish states, less measurements, so less operators, so in the subregions. So this is the meaning of the relative entropy, intuitively. Okay, so now it's time to introduce entanglement measure. So entanglement measure, so of course there are many entanglement measures, but one of the most well-known one is the entanglement entropy. So now I'm going to give you several examples. Okay, so entanglement entropy is a good measure. Probably, yeah, most of you knows the definition because it's given by the von Neumann entropy. For say, okay, let's consider some system A. Okay, A, okay, yeah. So then the entropy is given by rho A log of rho A. So rho A is reduced density matrix. So given some density matrix rho, and you take a partial trace over the complement system A bar. So this is the entanglement entropy, and the relation between entanglement entropy and relative entropy is as follows. So using the relative entropy, suppose you are working in finite dimensional system. So then the relative entropy, using the relative entropy, the entanglement entropy is given by this. So basically, so you compare the given reduced density matrix with the uniform states. So this is the uniform distribution or maximally entangled states. So this is so-called maximally entangled states. Okay, if you remember the partial ordering yesterday, so this distribution is the leftmost of the partial order. So it means that it is most entangled states. So you compare, basically you compare the most maximally entangled states to the given states, and the difference is basically given by, minus of the difference is basically given by the entanglement entropy. So this is some interpretation. And okay, another, okay, of course it satisfies all the axioms I wrote in previous pages. And there is a very important properties. Okay, so the consequence of the monotonicity of relative entropy is so-called strong subadditivity. Maybe I should use the other page. Okay, so from the monotonicity, of the relative entropy, you can prove, okay, you can derive so-called strong subadditivity. Okay, so when you talk about strong subadditivity, so usually you consider three disjoint systems. So A, B, and C. And of course, there is some other complementary region. So A union, B union, C union bar. Okay? So now you pick up three disjoint Hilbert spaces, A, B, C. And so you can define the entanglement entropy for each regions, and of course the entropy for the region, so say union of A and C, for example. So then the strong subadditivity means that means this. So this is a non-trivial inequality, so which follows from the monotonicity of the relative entropy. And basically, actually, so the strong subadditivity is actually equivalent to the monotonicity of the relative entropy. So the monotonicity, so SSA, okay, I will write it as a SSA, and monotonicity of relative entropy as a mono. So then SSA and mono is equivalent. So yeah, SSA is the most kind of strongest inequality known for entanglement entropy so far. And now, so let's move to another measure. So it is called the relative entropy of entanglement. So this is another example. This is another example. So example 2. So the relative entropy of entanglement is kind of very natural concept. Basically, so you are given pure space of quantum states, and so there is a subset, so denoted by X. So this is the subset of separable states. So this is the separable states. And suppose you are given some 1 point, so rho, and now so you want to measure the difference between rho and the separable states as a measure of entanglement. But okay, so now I'm going to define, say, the relative entropy of entanglement. So it is defined by taking infimum of the relative entropy between rho and sigma is separable states. So you take the minimum distance between the entangled states and the closest separable states. So this is very natural definition of the entanglement measure, and it is also known that basically it also satisfies all the axioms of the quantum measure, so entanglement measure. Okay, although it satisfies all the axioms, so it's not so useful due to this definition. So you have to take infimum. So even in quantum mechanics, it's not so easy to compute this quantity. But recently, especially when you go to the quantum field theory, so it turns out that it's not so clear how to estimate this guy. But there is one nice work, at least one nice work. So in quantum field theory, maybe I don't have time to explain their work, so I just quickly mention so what they did. In quantum field theory, so this relative entropy is studied by Hollands and Sanders. So they studied this measure in quantum field theory, but not directly. But so this measure is bounded by other measures from below and up from above. So they estimated this guy using such a bound. So this is one nice work. But anyway, so there is some measure given by using the relative entropy. And now, so let me briefly summarize what we have done. So let me comment on some relation between what we have done and the resource theory. So there is nice interpretation of quantum information theory as a resource theory. So basically, so we have dealt with are separable states, and we have operation, so LOCC or CPTP, so wherever they are, and we have also entangled states, Yes.
The LLCC operation is the same as the CPTP operation.
LLCC is a subclass of CPTP.
Subset.
Subset, yes.
So if the partial trace belongs to the CPTP, why do we believe that the theorem applied to the LOCC operation also satisfies?
I'm sorry, could you repeat your question again? So I could hear well. Yeah.
As a partial trace operation belongs to the CPTP operation,
yes.
But the theorem about the monotonicity of the relative entropy applies to the LLCC operation.
Mm-hmm.
So maybe partial trace is not a LLCC. So
I see, a partial trace. Yeah, maybe, yeah. It's outside of LCC. Yeah. Well, yeah, then, yeah, I should write CPTP here. Anyway, so you have some set of operations, so CPTP, and you have separable states, and you also have entangled states. And you have entanglement measure. Okay, sometimes quantum information theorists say that the entanglement is a resource. And what do they mean by resource? Okay, so that's what I want to talk about here. So basically, there is a theory of resource, and the resource theory concerned with free states, and they also have defined free operations. And also they also have resource, and they also have resource measures. So it's just a formal notion of resource. So resource measure. So basically, when you talk about the resource theory, so you first define so what you can do for free. So this is what I mean by free operations. So, and the resource, of course, means some non-trivial resource, so which is not available for free. But there are some free resources. So it's available for free. So, okay. But once you define free operations, then, so you can mathematically you can define what the free states are. And then, if you perform some operation, free operation on resources, then basically the resource will be consumed after free operations. So this is what resource theory deals with. And they also define, so you can also define the measure of resource, so the value of resource using resource measure. And there is one-to-one corresponds, of course, the QYT so, objects and resource theory. So you can interpret what we have done in terms of resource theory. So basically, the separable states are kind of free, because if you are given two states or system, you can freely make a tensor product of them. And you can make separable states for free. So yeah, taking tensor product is regarded as a free operation, for instance. And also you can do some local measurement, also LOCC or CPTP operations for free. So basically without having non-trivial resources. Okay, basically you are allowed to do CPTP for free. But the entangled states cannot be created by CPTP operation. You cannot increase the amount of entanglement by CPTP. So entangled states is initially kind of given for us. So that's why it is called resource. And what we have constructed as an entanglement measure is, of course, correspond to the resource measure. So entangled states can be regarded as a variable resources in this context. So, okay, of course, yeah, this is just a conceptual correspondence, but there are many instances, examples. so where resource theory is applicable. So for instance, you can reformulate thermodynamics for non-equivalent states in terms of resource theory. So there are this is very universal approaches to these questions. Okay, so, I think I haven't given you any references, so now it's time to give you some. Okay, so for the reference, for the first picture is that, so basically, I talked about the majorization theorem, and the majorization theorem is very well described by Nielsen's lecture notes, so it's available online. So I think it's available from his website. So this is one main reference for my first lecture. And so if you are interested in the entanglement measures, so there is a very nice review by Plenio Bermani. So it's available from archive. So it's quantum physics 05005. Okay, so it's available from archive. And so if some of you are interested in the resource series, so recently there appeared a nice review. So this is a review for quantum resource theory. Yeah. So the second one is the review about the entanglement measure. So you can find some axiomatic approaches to the quantum entanglement measures, and you can find more and more examples of measures if you read this review. Okay. Is there any question? So if not, yeah, I'd like to move on to the QFT side. Okay, good. So now, okay, let's move on to the quantum field theory. So what we have done is only in quantum mechanics. So we want to generalize it to the quantum field theory. And roughly, so there are two approaches. So when you go to QFT, so one is, you naively generalize quantum mechanical description of entanglement to QFT using so-called algebraic quantum field theory. So there is an algebraic formulation. And the other one is, of course, the path integral formulation. So algebraic formulation is very useful when you want, if you want to prove This is useful for proving non-trivial inequalities. But yeah, practically, so it's not so convenient because the objects are given as algebraically. So it's not so useful for practical computation. So on the other hand, path integral is highly useful in practical computation. So in this sense, probably you should be familiar with both methods, both formulations. Yeah. So basically, so what people are doing is that people basically kind of draw some implications from algebraic formulation of entanglement, and they use path integral formulation to obtain some non-trivial results. Okay, so maybe it's good to start with the algebraic formulation because it's very close to the quantum mechanical approaches. So let me start with algebraic one. So let's remind that, so when we define the reduced entropy matrix, so we define it very explicitly. So namely, so given a tensor product decomposition, so when we define a reduced entropy matrix for some subsystem A, so for a moment, so I assume that the tensor product decomposition also holds even in quantum field theory, but although it's not true in general. But anyway, so let's just consider this case. And so we define the reduced entropy matrix. So we define it very explicitly. So rho A is defined by taking a partial trace over the complement, so A bar. So this is, of course, the one definition, or very explicit definition. But there is another characterization of the reduced entropy matrix. So basically, from this definition, you see that if you compute some expectation value, so BEV of some operator localized on the region A, so you can, of course, compute it using the original density matrix rho. But more precisely, so OA means that this is some operator in Hilbert space, acting on Hilbert space A, and anyway. So this is some operator on A and identity operator in A bar. Okay, so this is a shorthand notation. Okay. So it follows from this definition that you can also calculate the BEV of OA using the reduced entropy matrix. So if I write it more precisely, so I should write it in this way. Okay. So since the operator is kind of trivial in the complement size A bar, so you can naively take a partial trace. Sorry, so this must be A. This must be A. Okay, you first take a partial trace over A bar, and then you end up with this expression. Okay, so this follows from the definition of the reduced entropy matrix. But this holds for any operator in the region A So in other words, you can define the reduced entry matrix such that row A satisfies this relation. So this is equivalent. Okay, so without defining, without using this expression, so you define row A directly through this relation. Okay. So this means that if your observation is restricted to the region A, then you do not have to know the information outside A. Basically, you only need all the information in the region A. So row A contains all the information inside A. So row A contains complete information as long as you're interested in the subregion. And you can also perform some unitary transformation. Okay, basically, so OA is of course invariant under the following unitary transformations. So let's apply some unitary on the operator. So it will be some time aberration. So you could be some time aberration, but it's localized in the region A. So you only acts on HA. And similarly, so let's evolve row A using the same unitary. And of course, the wave of OA doesn't change by definition. And of course, so you see that the entanglement entropy is also invariant. So what it means is that, basically, so if you act some some unitary transformation, which only acts on the region A, so then it doesn't change anything. So it means that now, so of course in quantum field theory, so we have time and space, and we need to deal them in equal footing. So this is my region A, and let's just consider some time aberration. So this is some time aberration. Acting on A, only A. So namely, so now, so we want to have another surface, another slice. Region A is originally defined at, say, t equal to 0. So this is t equal to 0. Oops. But so you can take some time slice. And then, so if, now, so this diamond means that this is a so-called domain of dependence. So let's define the domain of dependence of A. So this is the domain of dependence. So domain of dependence, everything inside domain of dependence of A is completely fixed by the information on A, Because, so my handwriting is very bad, but so this is 45 degrees, and this is also 45 degrees. So any information outside A cannot enter into the domain of dependence of A, So so this is any information in A bar cannot enter into the domain of dependence. So that means that all the information inside D of A is completely fixed by the initial condition on A. Okay? So now, so if A tilde has the same domain of dependence as A, then there exists some unitary. Okay, actually, I should write this one here. Anyway, there exists some time evolution on A acting on domain of dependence such that rho A tilde is unitary equivalent to rho A. Okay? Because, okay, even if you choose another slice like A tilde, the domain of dependence is the same. Okay, is the same as the original one. So all the measurements, okay, all information inside the domain of dependence is also uniquely fixed by the initial condition on A tilde. So yes, so this is the domain of dependence. So it means that, okay, you can take any slices which has the same domain of dependence as A, if you like, okay, to specify all the measurements, all the information inside DA. So what is important is that, okay, basically, the choice of A is not so important, but the domain of dependence of A is important. So once you specify some space-time region, then everything happens in some space-time region can be described by some algebra associated with this domain of dependence. Okay. So what I want to emphasize is that, okay, so rho A is also, of course, it contains every information, but rho A, okay, rho A appears to depend on the choice of the slice, but the important thing is that the important information is also contained in the algebra associated with this region. Okay. So now, instead of using rho A directly, so we want to associate an algebra to space-time region. So given some space-time region called U, now we associate. Okay, I don't want to give you a precise, rigorous definition of algebraic quantum theory, but roughly speaking, so you have the operator algebra A or A sub U associated with a space-time region. And given the operator algebra, so basically, okay, of course you need to specify the vacuum states. And but basically, so given the operator algebra, so you can reproduce all the correlation function over measurements it happens in this space-time region. So this algebra contains all the information. So this is the substitute for the reduced tension matrix in quantum mechanics. Okay. In the algebraic formulation of quantum theory, so you are given some operator algebra associated with space-time region. But of course, you need to impose several assumptions for the operator algebra. And so there are some postulates. Postulate. So if space-time regions, so one space-time region is included in another space-time region. Okay, U tilde is included in U. If U tilde is a subset of U, then the algebra of U tilde is also included in the algebra of U. this is very natural postulate, because if you shrink the size of the space-time, then you have less operators you can use. Okay, so this is very natural postulate. And probably some of you noticed that, okay, so this is very similar to the partial ordering we have seen in quantum information theory. Okay, so this is, okay, once you have a, okay, so actually, so this structure, the inclusion of space-time region is also a partial order. Okay, you can, okay, if U tilde is completely contained inside U, then you have an order between them. But if U and U tilde has a partial overlap, then you cannot compare these two space-time regions. So in that sense, this inclusion gives you a partial order. And this partial order also gives you the partial order for the operator algebra. So this is very similar to what we have seen in quantum information theory. So we had a partial order for quantum states. But now, so we have a partial order for the algebra or space-time regions. Okay, but anyway, so this is a postulate. So this is, but this gives you a partial order. Is it clear? Okay. So this is one postulate, and okay, of course, I cannot give you the full detail of algebraic QFT, and of course, yeah, by definition, I'm not qualified to give you all the details. But the recap is that, okay, if U and U tilde are space-like, separated, so namely, this is U and this is U tilde, and they are space-likely separated, like this. So then, the operator algebra is supposed to commute. So this is also a very natural assumption, okay? Because they are causally unrelated. So their algebra must commute to each other. And there are a few more postulates, but I won't give you any details. So anyway, so you need to impose some covariance for the algebras. I won't show you the details. Okay, anyway, you impose some covariance and etc. and the existence of vacuums and etc. But anyway, so there are some postulates, and if you are interested in, so maybe you can take a look at Haag's textbook. So it's called local quantum physics. But okay, anyway, but there are, okay, mathematicians studies these operator algebras very well, and they also have a nice classification. So classification of A. Okay, so it is known that there are 3 types. Okay, type 1, type 2, and type 3. Yeah, basically the classification was done by von Neumann. Okay, basically the type 1 corresponds to the quantum mechanics. So you have tensor product decomposition of your Hilbert space, and you can define trace. So this is a most familiar case to us. But okay, type 1 does not contain quantum field theory. So actually, the quantum field theory is in type 3. I think it's in type 3.1. Anyway, yeah. Type 3 does not have a trace. Or I would say, if you take a trace, then for any operator, then it becomes infinite. So in that sense, it's kind of problematic, but there is some approaches to study type 3 cases. So now, okay, let's but let's pretend that our system is type 1 for a moment.
Well, what is type 2?
Please don't ask me. Just Google. Yeah, type 2 cases, I'm not sure it is related to physics, but mathematicians are interested in these cases because there are some nice properties. So maybe it's useful for math, but not so useful for us. Okay, so let me move on to the relative entropy. So basically, so we want to define the relative entropy as in the case of quantum mechanics. But now, so we are kind of pretending that our system is type 1. So we can do the similar definition. But now, I'm going to give you new definition, which turns out to be equal to the previous one. So for, say, space-time region, okay, for simplicity, let's take a space-time region as a domain of dependence of region A, just for simplicity. So then, so we define the relative entropy for two states. So relative entropy between two states, say psi and phi. Okay, so these states are defined for entire space. So namely, so it's a vector in the total Hilbert space, not the subspace. Okay. So then you can define the relative entropy associated with, say, the subregion A as follows. So now you have two density matrices. Actually, so these density matrices, okay, actually I kind of define it as a pure states. So then the definition is that, okay, it looks weird, but it turns out that it's equal to the previous one. So now you have some minus of some bev of some operator, so log of some operator. So this delta is delta psi slash y is called so-called relative modular operator. But in type 1 case, you can give a very concrete expression. So you have rho phi, the resistance matrix of phi times rho psi in A bar. So this is a resistance matrix into the complementary region A bar. But here you have inverse. So this is called relative modular Hamiltonian. So actually, yeah, if you substitute this expression into the definition, and then so you can show that it reduces the previous one. Okay, let me show you how it works. Okay, by the way, okay, this is of course the story in type 1 case. But the reason why I introduced such an operator is that, okay, you can generalize this construction to the type 3 case. So I will comment it later. So, okay, so I'm going to show you that, okay, first, okay, I'm going to show you the following fact. So actually, this appears to be a bit different from our previous relative entropy. But now I'm going to show you that, okay, previously we defined the relative entropy between two states, rho and sigma. But this one, so what I just defined is equivalent to the relative entropy between the reduced entropy matrices of psi and phi. Okay, I'm going to show you how it works. So the proof is that it's just very elementary. So the left-hand side is by definition. Okay, so let's remind that I define rho psi as a pure state. So okay, so now you have a wave using psi, but you can make it as a trace of rho psi or times log of delta. So this becomes minus trace of rho psi log delta. Okay, so then you substitute so this expression. So you just take a log of this guy. Then actually, okay, if you take a log, then it becomes log of rho phi a times identity operator, and the identity times log of rho psi. So of course, this minus sign comes from the inverse of the density matrix. Okay, so now I'm taking trace of a whole space, but since first let's evaluate the first part. Okay, so here, so you have tensor product form. So previously, as we discussed in the computation of the wave of some operator localized on A. So okay, so we do the same thing. So basically, the first part reduces to minus trace of over A, and you have reduced entropy matrix. So this is the first term. Okay, I take a partial trace over A bar. Okay, and from the second, so you do the same thing, but now, okay, you need to take a partial trace over A, not A bar. So you end up with trace over A bar and rho psi A bar log rho phi A bar. Sorry, psi. Okay, so far so good. But now here we have A bar. So, but okay, if you remember, okay, this is actually equal to the von Neumann entropy for the region A bar. But now we are dealing with the pure states. So actually the entanglement entropy, or in the region A is equal to the entropy of A bar. So it follows from the Schmidt decomposition. So if you remember the Schmidt decomposition, then okay, yeah, you can prove it very easily. So this part using the Schmidt decomposition equal to the same expression, but A bar is replaced with A. Okay, if you use the Schmidt decomposition form, then you can convince yourself that you can switch the role of A and A bar. So this follows from Schmidt decomposition. So finally, so what we get? is that, this is the end of the proof. Once you flip the role of A and A bar in the second line, then you end up with the original definition. Okay, for safety, let's just write everything. So you have rho psi A times log of rho phi A, and in the second line you get trace over A and rho psi A times log of rho psi A, and you just combine two expressions in one line. Then you have log of rho psi A minus log of rho phi A. And this is what we defined as a relative entropy with argument given by the argument rho psi A and rho phi A. Okay. So this is the end on the proof. Okay. So, yes?
In this proof, you treated A as a portion of the total Hilbert space, right?
Mm-hmm.
Instead, few slides before, you were treating A as a portion of the space-time. How the two are related?
Sorry, here, so A, okay, my definition, my new definition here depends on A, space-time region, subregion.
Okay.
Okay.
And how I map this space-time region to a portion of the total Hilbert space?
Well, yeah, that's a good question. So basically, this relative modular Hamiltonian is defined for the whole space, not only for a subregion, A and A bar. So, okay, it is operator acting on total space. Yeah, and this state also is a vector in Hilbert space, total Hilbert space. So psi and phi are vectors in total space, total Hilbert space.
Okay.
Okay. So, but if you if you naively substitute this expression of the relative modular Hamiltonian, you can take a partial trace.
But what does it mean taking a partial trace over a space-time region?
Well, now I assume that some Hilbert space description. So yeah, it's just a Hamiltonian picture. Is it clear?
I will think about it. Maybe I will ask you again.
Okay.
Okay,
Yeah.
thanks.
Yeah.
Is this proof?
Sorry, how much time do you have? Sorry. How much time do I have? 2 minutes? 3 minutes? Okay. Yeah. Any question? Yes.
Is this modular Hamiltonian only valid for
So
type
could
1?
you speak up? Sorry.
Is this proof valid for only type 1 case or?
Okay, this is a story for type 1. Yes, I should emphasize it. Okay, so this proof, so this is a case, for type 1. And in the type 1 case, so this new definition reduces to our previous one. But this one can be generalized to type 3. So this is, I think this is called Araki's relative entropy. So this is defined by Araki. I don't know, maybe 70 something. Very old paper. But this is the case for type 1. And but the definition of relative entropy, so the definition of the new definition. New definition of relative entropy is valid for type 3 cases. So yeah, actually, yeah, that's the motivation why Araki introduced this definition in his paper. And actually, but to study the relative entropy in type 3 case, you have to use so-called Tomita-Takesaki theory. So there is, yeah, well, it's completely math, yeah, literature, but okay. Let me finally give you, okay, let me finish in 1 minute. So let me give you some reference about these things. Okay, the most accessible one is a review paper by Witten. So he has a nice review explaining all these things. Okay. So he explains, yeah, basically he started with quantum mechanical case, and he also talks about algebraic formulation of quantum field theory. So basically I followed his lecture notes, today. If you are interested in, you should take a look at his review paper. And then, so you can also find the detail of Tomita-Takesaki theory. Okay, so maybe I finish here, and tomorrow I will continue to discuss about quantum entanglement in quantum QFT, especially using passive integral. Thank you very much.
Maybe just one or two more questions, if you use microphone.
For quantum field theory, why you can write the Hilbert space as a tensor product of a subregion A and A bar?
Yeah, good question. Yes, in gauge theory, okay, if you just have a free scalar theory, for example, so then the tensor decomposition is trivial because, free scalar is just harmonic oscillators on lattice if you discretize it. But if you have a gauge series, then the degrees of freedom are living on link variable on lattice. So, but you have to cut the links to divide your Hilbert spaces. So then it's not clear how to decompose your Hilbert space for the gauge series. So you have to slightly enlarge your Hilbert spaces such that it is consistent with tensor decomposition. And then there is a kind of ambiguity for the decomposition for the gauge series. Yeah.
Okay, thank you.
Okay. So any?
In your new definition of relative entropy, the rho psi A bar is necessarily invertible?
So this one or this one?
This one, rho psi A bar. Is
I
it
assume,
invertible?
I assume so. Yeah, it's invertible. Yes, it's positive operator. Yeah, and invertible. Yes.